Visual coherence in mixed reality is a key element to plausibly present virtual objects within the user's real-world environment. However, naive rendering of virtual information may easily break the visual coherence and thus prevent the user from immersing in the mixed reality environment. Current mixed reality rendering pipelines only match the field of view of the physical camera and omit important camera characteristics such as color, noise, blur, and built-in image enhancements. We present a series of networks for increasing the visual coherence for video-based mixed reality applications. The proposed networks mimic the characteristics of real-world camera components by learning the visual characteristics of a camera pipeline and applying these characteristics to renderings of virtual objects. While previous approaches either focus on a specific camera or on a specific component of the pipeline, we introduce the first system that jointly simulates all major components of an arbitrary modern camera. In our method, a traditional rendering approach using a pinhole camera provides an initial rendering within a calibrated color space. We then apply 3 networks as a post-rendering process within the overall rendering pipeline. The series of networks map the calibrated rendering of virtual content to the displaying color space by introducing the unique characteristics of the physical camera, such as blur, color tone mapping, and noise to the rendering. Our first network, LensNet, blurs the initial rendering according to a pixel's depth and the real camera's focal length. We use a Gaussian mixture model to render high-quality blur, and we train LensNet to find the parameters of the model. For training the network, we capture images of a planar tracking target at several distances while varying focal lengths. We add noise to the initial rendering and we map rendered colors to the color space of the real camera, in order for them to match the appearance of a captured object. We find the mapping using the second neural network, SensorNet, which we train with pairs of rendered and captured colors. Finally, we apply ISP-Net for compositing real and virtual content and for mapping the colors and noise to output color space. We train the neural network using a dataset of raw and output image pairs, so that the network could learn the behavior of the camera image signal processor.